Hi guys, and today we will be doing section 3.1, and we're going to talk about relations and functions. So the objectives for today are understanding the definition of relations and functions, determining whether an equation represents a function, using function notation to evaluate functions, vertical line tests, classifying functions, and determining the domain of a function given the equation. So there's a lot really in this section, and we will go over it. So the definition, I'm going to read the definitions, and then I'm going to explain the definitions, because sometimes mathematical definitions are confusing to people. So a relation is a correspondence between two sets A and B, such that each element of set A corresponds to one or more elements in set B. So if we call set A the domain of a relation, and B is called the range. So I'm not sure that makes any sense to anybody. So what I'm going to do is I'm going to give you another explanation. So if we have what we really are talking about for this section is a set of ordered pairs. So we have an X and a Y, okay? The X value is always the domain, and the Y value is the range. And I could have, there are different sets. Like, let's say I have a set A where the numbers are 1, 2, 3, and 4, and set B, and we'll call this the domain, and set B 3, 5. Well, how these two sets relate to each other is by ordered pairs. So I could say, well, let's take 1 and 3. That's an ordered pair. I took the first number from the domain, which is X, and I took the second number from the range, which is Y. So this relation has a 1, 3. So it is a relation because we are relating two different sets, and we're putting them kind of together for what they correspond to. I think that may work. If not, you can always email me and ask me questions if I don't get to your question in a lecture. Feel free, because sometimes I'm not sure what you're not sure about, where is like, because it's not a live class. So it would make me very happy if you had a question. If you would, you can call me, you have my number, you can text me, you have my number, or you can send me an email. I'm sure you have my email. Okay, so now here's a visual representation of a relation. So on the left, we have the domain, and on the range, we have the range. And we call this really the independent variable. And we call this the dependent variable. And sometimes I'll refer to it like that, and sometimes I won't, but that's another way to talk about them. And of course, also X and Y. So if I look at this picture, I can see Adam, and I follow the arrow, weighs 180 pounds. Patrice, if I follow the arrow, weighs 190 pounds, and Scott weighs 180 pounds. So this is just a visual representation of a relation. I could even write it as an ordered pair. I can say Adam, comma, 180. Patrice, comma, 190. And Scott, comma, 180, right? And now I have an ordered pair. I have two sets, and they're related. Or I can turn them backwards. So suppose that a delivery man was to deliver a package to the roommate who weighs 180 pounds. Well, because there are two people who weigh 180 pounds, I don't really know who I'm supposed to give it to? Am I supposed to give it to Adam or Scott? Because both of them, as you can see, weigh 180 pounds. So this is because the element of 180 pounds is associated with two distinct elements in the range. And we say that this relation is not a function. And I'm going to explain, I think, in a better way, what makes a relation a function. So one important thing it's saying is for a relation to be a function, every element in the domain must correspond to exactly one element in the range. So here, what I'm going to do is, no, I'm not going to do that yet because we're going to talk about what is a function. We know what a relation is, right? But now we need to define what's the difference between a relation and a function. And here it says a function is a relationship such that for every element in the domain, there's exactly one element, corresponding element in the range. Or if this is helpful, another way to say it is for every value of x, there is only one value of y. Okay, so this is important. For every value of x, there's only one value of y. So if you tell me what x equals, I can tell you what y equals. Okay, if I can't, then I don't have a function, but I still have a relation. So I'm going to give you examples here, which I think will help. So, for example, let's see. So let's use credit card numbers and people, okay? So this is the domain, and this is the range. And I'm not going to, credit card numbers are really long. I'm not going to put long credit card numbers. I'm going to put short credit card numbers. So I can say like 1, 2, 3, 4, 3, 4, 5, 6, and 5, 6, 7, 8. Okay, so I have 3 credit card numbers. And then people, Jim, Mary, and Tom. Okay. So, and actually, I'm going to copy this before I do other things to it. So let me copy this. Copy, and we'll paste it. And we'll paste it one more time. So I'm going to give you 3 different examples. Okay. So all of them have the same information to begin with. And the first one I'm going to say, well, I'll make it easy. The first credit card belongs to Jim. The second credit card belongs to Mary. And the third credit card belongs to Tom. And remember, what a function means is that for every value of x, which is in the domain, or I can say this is x and this is y, for every value of x, I only have one value of y. Well, that's true for this first example, right? This right here. I look at x, it goes to one value. I look at x, it goes to one value. I look at x, it goes to one value. So this is a function because for every x, there's only one y. All right, now let's look at the next one. So let's say I do this one and I say this, I'll make arrows. So now, is this a function? Well, it's not. This is not a function. And let me explain why. So that 1, 2, 3, 4 actually belongs to Jim and Mary. And let's say that Jim and Mary don't know each other. Okay, they're not on the same credit card because they're husband and wife or anything like that. They don't know each other, but they both have the same credit card number. Well, as you can see, that's not really a very good plan from the bank, because first of all, who knows, like, who's going to pay, right? Like, if Mary doesn't feel like paying, then Jim has to pay the whole thing, or he won't pay his credit card, even though Mary could have used it, or vice versa. So, and let's give another example. If I find that credit card 1, 2, 3, 4, like I'm walking down the street and it's on the ground, I pick it up and I'm like, oh, I found somebody's credit card. And what am I going to do? Well, I'm going to turn it over and I'm going to look at the phone number on the back. And I'm going to call them and I'm going to say, I found a credit card. And they're going to say, well, what's the credit card number? And I'll say 1, 2, 3, 4. And I'm going to say, oh, yes, I see. That belongs to either Jim or Mary. Well, that's not a very good plan, right? Because you don't want, like, if you're Jim, you don't want Mary using a credit card and you're not knowing that she has exactly the same credit card number, and you're going to get billed for it, or she's going to get billed for yours, or who's going to pay the bill. I mean, you can see that there's a lot of problems in two people having the same credit card number who don't know each other. So we can see that if I look at my X value or my domain, and I look at 1, 2, 3, 4, I literally have no idea who that belongs to. It's one of two people, or, you know, it could be 10 people, but no matter what, it's not a function. Okay. So now let's look at one more example. Let's say I do this. Okay. So now 1, 2, 3, 4 is pointing to Jim, 3, 4, 5, 6 is pointing to Jim, and 5, 6, 7, 8 is pointing to Tom. Now the question is this a function? Now, often I hear, no, this is not a function, but this is a function. So why is this a function? Well, if I find 1, 2, 3, 4, the credit card 1, 2, 3, 4 on the ground, who do I know who it belongs to? I do. It belongs to Jim. 3, 4, 5, 6 belongs to Jim. 5, 6, 7, 8 belongs to Tom. I actually, for every value in X, there's only one value in Y. Or for every value in the domain, there's only one value in the range. Even though Jim has 2 credit cards, that's okay. That doesn't make it not a function. He just has 2 credit cards. Okay, but I know where each thing goes. So basically, if I pick an X, and when I do whatever I'm going to do with that value, here it was credit cards and people, it could be an equation, it could be other things. Phone numbers are a good example. I want it to go to one place. I don't want to call somebody and have it go to 2 different people. I don't even know who's going to pick up, right? So something like that would not be a function. So again, let's talk about, for every value of X, there's only one value of Y. And that's what we said. For every value of X, there's only one value of Y. And hopefully this is clear. So let's go to our first example. Determine whether each relation is a function and then find the domain and range. So let's look at A. Is A a function? Well, do I know how tall Phoebe is? Yes, 5'5". Amy, 5'5". Katie, 3 feet 1 inch. So this is a function. And my domain is the X values, where they're starting. So in my domain, I have Phoebe, Amy, and Katie. And then in my range, I just have 5 feet 5 inches and 3 feet 1 inch. So there's my domain and range. This is a function and all is good. Okay. Now look at B. Is B a function? So I just want you to think about it before I answer. And well, it's a function. So why is this a function? Because if I ask you where 0 goes to, it goes to 7. 3 goes to 7. -2 goes to 7. 6 goes to, they all go to 7, but they all, like, none of them go to the same number, doesn't go to two different numbers. This is different numbers go to the same number. That's a little different, right? So the domain here is 0, 3, -2, and 6. And the range is just 7. And both of these are functions. Okay. Now, what if you're just given a set of a paired, this is a set of ordered pairs. So let's make a little chart. I'll show you how to look at it without the chart in a minute, but let's just look at it with the chart first. Here's my X, here's my Y, and I'm not going to repeat any values. So what do I have for X? I have 3, -3, -4, 1, and 3, but I already have 3. And then for Y, I have 7, 2, 5, 1, 4. 5, 4, -4. Is that right? 7, 2, 5, 4, -4, 3, -3, -4, 1. Yes. Okay, so now let's put in our little arrows. So 3 goes to 7, -3 goes to 2, -4 goes to 5, 1 goes to 4, and up 3 also goes to -4. So is this a function? It is not a function. Why is it not a function? Because if I ask you what number, when I put in 3 for X, what is my Y value? Well, I have 2 different Y values, and that's not okay. So that makes it not a function. And a way you can look at it just from the list is I have a 3 for X, and here's another 3 for X, but notice they both have different Y values. If they had the same Y value, it would really be the same. But since they have 2 different values, I don't know how to graph 3. I have 2 values. It makes it not a function. So now if we just look at the numbers and don't make a table or a little chart like that, well, let's see what we have for X's. I have -1, 0, 1, 2, 3. Well, I only have one of each X. It doesn't matter if they go to the same Y, right? But each X has to know where it's going, and it can't go to the same Y. So this is a function. If you didn't understand what I just said, then that's okay. We can always make a little table here on the side. And I'm going to put my X values, -1, 0, 1, 2, 3. My Y values, 2, I have another 2, 5, 3, and I have another 2. So that's really all I have for my Y values. So let's put little arrows. 1 goes to 2, 0 goes to 2, 1 goes to 5, 2 goes to 3, and 3 goes to 2. I'll just wrap it around like that. So if I ask you where -1 goes, it goes to 2. If I ask you where 0 goes, it goes to 2. If I ask you where 1 goes, it goes to 5. If I ask you where 2 goes, it goes to 3. If I ask you where 3 goes, it goes to 2. I don't have 2 different values for Y with the same X. Okay, so this is a function. And you can tell because, first of all, you haven't repeated any X values. So even if the y values are the same, it doesn't matter. We do have different functions where you want it to go both ways, but just a function is not it. That's called a one-to-one function, and we probably will be studying that later in the semester. But for just it to be a function, every x can only go to one y, okay? But the reverse is not true. So let's look at this example. It says use the domain and range of the following relation to determine whether the relation is a function. Well, first thing I have to do is I have to write my ordered pairs, right? So my first ordered pair is -4, 5. That's the circle. Then I have -2, 2. Then I have 0, 0. I have 1, 4, and I have 1, -2. Now, without really doing much more work, I can see that for x equals 1, I don't know which value I'm supposed to pick, right? It's not a function because if I ask you what number, when x equals 1, what is y equal? Well, you'd have to say 4 or -2. And that's not a function because we have to be able to say either 4 or -2, right? We want to know one place it goes. So now we want to determine whether equations represent functions. So we're now going to not look at graphs, but we're going to look at actual equations. So to determine whether an equation represents a function, we must show that for any value in the domain, there is exactly one corresponding value in the range. How do we do that? Well, first, I think the best way is solve for y. Okay, so if I solve this first a for y, I'm going to subtract 3x from both sides. And I get -2y equals -3x minus 12. And I add 12 to both sides. No, sorry about that. I'm trying to solve for y, so I'm going to leave that there. Another thing that I would do is, since every one of them is negative, I can just multiply at both sides by -1, which gives me 2y equals +3x plus 12. And then I'm going to divide everything by 2, and I get y is equal to 3/2 x plus 6. Okay, so this is a function because no matter what value I put in for x, I'm going to get a different y. There's no x that I can put in that would give me 2 different y values, right? I'm only going to get one y value from this. So this is a function. Okay, let's talk about the second one. Well, the second one's already solved, so I don't have to solve for y. But no matter what value of x I put in, I'm going to get a different value of y. Let's just try, because the only thing that would be, so if it was just x squared, that wouldn't be true, right? No, it would still be true because I'm talking about for every x, I get a y value. But that y value, the y values can be the same, but not if I put an x value, I can't get 2 different y values. So, for example, no matter what I put in here for x, I'm going to get a value of y. And as many times as I put that value in, I'm going to get the same value, right? It's not going to change. So this is also a function because whatever value I put in for X, I get one value of Y. You're not going to give me two different values of Y, right? It's just going to equal something. C is a little different, and let me show you why. So again, let's solve for Y. I'm going to subtract X plus 3 quantity squared from both sides, right? So I end up with Y squared is equal to 16 minus X plus 3 squared. Well, I haven't yet solved for Y. To solve for Y, I have to take the square root of both sides, don't I? And when I do that, don't forget, I have this plus or minus the square root of 16 minus X plus 3 squared. Well, this actually means I have two equations. Y equals positive the square root of 16 minus X plus 3 squared, or Y can equal negative the square root of 16 minus X plus 3 squared, right? Because if I square both sides, I get Y squared equals 16 minus X plus 3 squared for both of them. And the negative times a negative is a positive, so it doesn't matter. But I can put in the same value of X for both of these equations, and I'll get two different values. I'll get a positive one, and I'll get a negative one. So for one value of X, on C, I have two different values of Y. So that would make this not a function. Okay? So now we want to talk about function notation, and I know sometimes this really confuses people. So I will read it, and then I'll explain it. So instead of using the variable Y, we use letters such as F, G, H, and whatever, really anything you like. These are commonly used for functions. F, G, and H are most common, but you can use other letters. If we want to name a function F, then for any X value in the domain, we call the Y value F of X. So basically what this says is Y is the same as F of X. Okay? That's what this second paragraph means. Third paragraph, and I'm gonna read it. So F parentheses X parentheses is read F of X. Or we can say the value of the function F at X. This is function notation. And let me add here, basically what this means is, let me see how to say it, F of X. So if I plug the X into my equation, I get Y, right? Normally, but that's the same as F of X. And I'll do some examples so you'll see better what exactly I mean. And this is real important. A lot of people get this confused. So F of X does not mean F times X. It is a notation that refers to the value of a function at X. So basically, if I were to use my function notation and I had an XY ordered pair, so if I say this is my ordered pair, that's the same as F comma F of X, because F of X is the same as Y. Okay, and I'm going to show you how to use it. I don't really like this slide, So I think what I'm going to do is skip it. And I'm going to skip that. I'm going to actually do, I guess I could do something with this, but I don't want to, I don't like when answers are already there. So let's get a new slide. I'll just show you kind of what they're doing here. So, I think I left the piece. Yeah, I left something here. Okay, so let's say I have this, and my equation is 3/2 x plus 6. So we have x, we have f of x equals 3/2 x plus 6, right? And then we have the ordered pair. So without looking back, let's see how this works. If x is equal to, let's say 3, I'm just picking numbers. Actually, let's make it easier even. Let's say x is equal to 2. Then here, what I'm saying is f, and everywhere there's an x, I'm going to replace it with 2. So I have f of 2 is equal to 3/2 times 2 plus 6. So the 2's will cancel, and I get 3 plus 6, which equals 9. And my ordered pair would be 2, 9. So I still have my x value. I plug it in. Instead of getting y, I'm actually finding f of 2. Okay? And I'm evaluating it. I'm saying, what is y? Basically, if I say f of 2 equals what, I'm saying, what is y when x equals 2? Okay. I think that's clear. Let me see. Let's try one more just for the heck of it. So if I say x equals 1, let's go through the whole process. So x equals 1. Let's do this. So when x equals 1, and I have my function, and what I'm going to do is I'm going to write it like this twice. 3/2 x plus 6. So why am I writing this like this? Well, notice instead of writing x, what I've done is write just parentheses, okay? And so for the actual function, this is filled in with x. And whatever is inside that function has got to be repeated, okay? But if I ask you what is, for example, we're saying x equals 1, now I'm replacing x with 1. And here, same thing. So whatever I replace it with replaces the x. And I always put parentheses wherever there's an x. So now I can evaluate this. This is 3/2 plus 6, which equals 3/2. Get a common denominator. 6 is 12/2, which is equal to 15/2. So that is my y value. My ordered pair would be x equals 1, y equals 15/2. Okay? So basically, that's how function notation works. This is just a graph of that, so we don't need that. So let's answer these questions. So first it says, rewrite these equations using function notation where y is a function of x. So first I'm going to solve this for y, and I'm going to add y to both sides. So I get, if I add y and I add y, I get 3x equals 5 plus y. And then I'm going to subtract 5 from both sides, and I get 3x minus 5 is equal to y. Now you could go the other way. I just had that negative y, so I just felt like making it positive by moving it to the right. But if you feel more comfortable moving moving y's to the left and everything else to the right, that's fine as well. So here's my equation with y, but what I'm going to do is change y. I'm going to put this in function notation, which means y is equal to f of x, and f of x equals 3x minus 5. Okay? Now it says, what is, you know what, I'm going to make a new slide here. Hold on. Let's do this right here on the other screen. Okay. Oops. I don't know where those other little things always come from. So let me cut that. Hold on, I'm sorry, give me a sec. Okay. Okay, so now we have f of x equals 3x minus 5, and we want to know what is f of 4. So again, I'm going to do it the same way that I showed you before. Everywhere there's an x, I'm just going to put parentheses. So I have f of x, but I'm going to leave the x out. And then I have 3 times parentheses minus 5. And if I'm being asked, what is f of 4? That means, well, actually, I said write it twice. So let me write it twice, sorry. So normally, the original equation inside here is an x, right? But now we want to know what is f of 4. So that means x is equal to 4. So I put a 4 here, and everywhere there's an x now, I put a 4. And then I just solve it. So I have 12 minus 5, which equals 7. So I now know that I know what f of 4 is. And if I want to write this as an ordered pair, I say, well, x is 4. And when I put in 4, I get 7. So this is my ordered pair. Okay? So it's still xy, or I can say x comma f of x. Same. Okay? Could be g of x, could be h of x. It doesn't matter. That's function notation. So what mostly confuses people about math who don't like math is there's a lot of notation that you have to understand. So to some people, it looks kind of like Chinese, right? Because there's all this notation. But if you think about it, what f of x means is a lot. So if I were to write, and I'll write it here just because I have some space. So f of x is the same as saying, what is, well, let me write it differently. So let's say I want to know what f of x, but this time I'm going to say f of 4. Okay, so what f of 4 means is, what is my y value when x equals 4? So that's a lot of words, and I can put that into a very simple notation. So I don't have to continually ask, what is y when x equals 4? I can just say what is f of 4? And that's why math sometimes people have problems with, because they don't understand the notation. So hopefully that makes sense. Now for B, it's asking me, does this point -2, 1 lie on the graph of this function? Now, remember in the last one, I said everywhere that you have an X, just put a parentheses. There's a reason for it. And some people don't know the exponent rules very well. So let me kind of go over those really quickly. If I have -3 squared or -3 quantity squared, are these the same? And the answer is no, they're not the same, because exponents only act or apply. I like that word better. I would say act. Only apply to what they are next to. So because of that, the parentheses are really going to make a big difference, because this right here, well, the exponent is next to the 3. Is it next to the negative sign? No. So really what this means is negative, and then I only square 3, so that becomes 3 times 3, which equals -9. But this one, when I ask you what is the exponent next to, it's next to the parentheses. So I make whatever's in the parentheses squared, or I multiply it times itself. And now I have negative times a negative is +9. So parentheses make a big difference. That's why here I said replace the values, the places where X are, just with parentheses, because if you don't, you might get the wrong answer. So for example, here I have this point, which means I'm going to plug in X equals 2, because this is still X comma Y, right? So I plug in -2. Well, if I do -2 squared without parentheses, notice it would be negative. But what I'm doing is replacing my X's in parentheses with whatever X is. So it becomes -2 squared minus 2 times -2 plus 1. And now I evaluate. So -2 squared is 4. -2 times -2 is +4 plus 1, right? And then this equals 9. But then this is my Y, or my f of X, whatever you want to call it. But it should be equal. If this was true, then my ordered pair is not okay, hold on. So when I plug in those values of -2, I get 9. I don't get 1. So that means this point does not lie on this graph. No, because I should have gotten, instead of this 9, I should have gotten a 1. If I got a 1, then that would mean that it worked. Actually, let me rephrase that. So ignore what I just said. But I'm close, because when I plug in -2 to this equation, isn't it supposed to equal 0? But it doesn't equal 0. It equals 9, which means that it's not, that point is not on that curve or on that graph. Okay, if this came out to 0, then it would be true, because when I plug in -2, I should get 0. Okay. And again, I made a mistake. So let's erase this and do it again. I still get a no probably, but I definitely did it wrong. Hopefully you caught me. Because I wrote that y as an x, but it's not. So here, let's do it again. I have -2 squared minus 2, but now I have y not x. So my y is 1 plus 1. Now this is supposed to equal 0. If this equals 0, then those points work for that equation. If they don't, then they don't work. So this is equal to, again, +4 minus 2 plus 1, which equals 4 minus 2 is 2 plus 1 is 3. So I can say no. This point is not on the point -2, 1 does not lie on the graph of this function. Because if it did, this should equal 0. But it doesn't, okay? So the answer is just no. Sorry about the mistake. Hopefully you can ignore the mistake and see what I really meant. Okay, so rewrite these equations using function notation where y is a function of x. And why we say that is because we could have, let's say we have f of x. Let's say it's equal to 2x plus 1. Well, then f of t, now this is an equation which is a function of t. And now I would put t plus 1 because my variable is this t. Okay? So when it says where y is a function of x, I'm looking at this. It could say where y is a function of t, and then I would have the bottom. Okay, so then answer the following questions. Well, again, let's start by solving for y. So we subtract 7 from both sides, and I get y equals -7. When I put it into function notation, I have f of x is equal to -7. So now let's take a look and see what happens. Let's put a little chart here. Actually, let's do a graph and a table. Okay. So when x equals, let's say x equals 3, what is y equal? Because that's what it's saying. What is f of x what is y or f of x when x equals 3? Well, if I have this, notice, even if I put a 3 in here, I don't have nothing's on the right is going to change, is it? Because I don't have an x there. So no matter what value x is, y is always equal to -7. So when x is 3, y is -7. When x is 5, y is -7. When x is 27, y is -7. When x is -13, y is -7, right? It doesn't really matter because you can see that the f of x or the y value is not dependent on x here. So I'm not going to graph all these points because I don't want to go that far, but I can see that so let's make this -7. So when x equals 3, -7. I should have put different numbers. When x equals 0, it's also -7. So -7, -7. And no matter what value of x I put in, I get -7. And I can connect these dots and notice what I get is a horizontal line, which is a line. So it's going to follow y equals mx plus b, where m is the slope and b is the y-intercept, right? So if I have a horizontal line and the slope represents the slant of the line, this is not a slanted line. So that means m equals 0. right? Because this is gone, m equals 0. And what I get is y equals b, which is the y-intercept, which is -7. So y is going to equal -7 no matter what x equals, right? I could also rewrite this as y equals 0x plus b, or plus, sorry, -7. And then hopefully you can see that no matter what x I plug in there, I always get y equals -7, which is the point. All right. So let's evaluate. And again, I'm going to do it the long, you do not have to do it my way. I promise it will work if you know what you're doing. If you aren't sure what you're doing, just do it my way. I promise it'll work. This is squared x minus 1. So notice all I did is I copied the equation. Everywhere there was an x, I just left parentheses. Okay, so the first one, if I plug in x here, I can see that f of x equals x squared plus x minus 1, just like it started with. But if I plug in 0, then I get 0 squared plus 0 minus 1, which is equal to -1. And that's it. Okay. So again, let's do it. So I'm not going to rewrite the original because we can see it up above us, but this is still squared plus x minus 1. And now what goes into my parentheses is -1. So f of -1 equals -1 squared minus 1 minus 1. And remember when I talked about exponent rules, I talked about it because without the parentheses, that would be this would be -1. But with the parentheses, it's +1. So it makes a big difference. So I'm going to square -1 and I get 1. Plus a -1 just becomes -1. -1 equals -1 because 1 minus 1 is 0. 0 minus 1 is -1. So that's basically how you evaluate these things. Okay, so this is going to take a little bit more work. Let me slide a new page in here. And all this. And I will move D to the next page. Okay, so we start here, and again, we start with our original equation, x squared plus x minus 1. So f of x equals x squared, what is it, plus x minus 1, yeah, plus x minus 1. So I'm going to say this, I'm just going to replace all my x's from here with parentheses, right? I think, yep, that's right. And then I'm going to fill it in with x plus h. And then I'm going to fill this in with x plus h. And I'm going to fill this in with x plus h. So this is what it equals. Now let's simplify. So x plus h squared, and let me put it over here to the side. I just talked about it. The exponent works on whatever it's next to, and here it's next to the parentheses. So x plus h squared is the same as x plus h times x plus h. And there's a simple formula for this. Again, I don't want you to memorize things, so you can always FOIL this. But if you like memorizing, then I'll give you a formula. So if you have a plus or minus b squared, okay, so it does, I have an a and a b, and it's going to look exactly like it does up there. This is going to always equal, and I'll write it out for you so you see. So if I have plus, then I have this, and then if I FOIL this, I get a squared, outer, AB, inner, AB, and last, B squared. And notice, because I have the same thing multiplied together, the middle terms are always going to be the same. And I'm going to get a squared plus 2AB plus B squared. And if it was minus, you'd get minus 2AB, right? So if it was a minus b times a minus b, you would get, let me see how I want to write this. I would get a squared minus ab still plus b squared. So I'd have a squared minus 2ab plus b squared. Okay, so the only thing that's changing with the signs is plus or minus, depending on whether this is a positive or a negative. So when it's positive, everything's positive. And when it's negative, then only this one is negative. Okay. So now, if you know that formula, you can just say this equals x squared, because a is x and b is h. So I have that plus 2xh plus h squared. And I don't have to FOIL it every time. But again, you're very welcome to FOIL it every time. So x plus h squared, we already know, I wrote it here, is x squared plus 2xh plus h squared. That's the first term. I'll put parentheses. So that's that, plus x plus h minus 1. And I can take all my parentheses off because I have nothing negative here. And I actually can't see anything that are like terms. So that is the final answer. I don't see anything to combine here, right? So this is the final answer. Okay, so now what we're going to do is I'm going to copy this answer so I don't have to do it again. Let me try one more time. Nope. Let's see, is that? Oh, I see, it's all together. Okay, let me see. Copy, paste. And what I'm going to do is I'm going to get rid of, let's see, can I do it? Let's see, ungroup. Okay, so now I should be able to just get rid of, I'm so lazy, right? And I think I did it. All right, so let me group them back together so I don't have to worry about that. Group. And now they're just one thing. And so we found out that this is what f of x plus h equals, right? Okay, but we're going to do this equation. This is actually a very special equation. It's called the difference quotient. You may or may not use it again. If this is your final math class, you will probably not use it again for anything. If it's not, you will use it when you get to your calculus class. So I know what f of x plus h is. Let's plug it in. We have x squared plus 2xh plus h squared minus x, plus h minus 1. Okay, so that's my f of x plus h. Then I'm going to subtract my f of x. Well, f of x is x squared plus x minus 1. X squared plus x minus 1. And I'm going to divide this whole thing by h. Okay, so hopefully this is, I mean, I know that it looks complicated, but we're just going step by step. It's not that bad. Let's remove all the parentheses. So I get x squared plus 2xh plus h squared plus x plus h minus 1. And then I'm going to distribute that negative. So I get minus x squared minus x plus 1. And this whole thing is again over h. So let's see what I get. Let's combine like terms. Well, notice I have x squared minus x squared. That's 0. That just goes away. And I have plus x and minus x. Again, just 0 goes away. Minus 1 plus 1, again, is 0. So it's gone. And let's just pick the ones I have left. So I have 2xh plus h squared plus h. And it looks like everything else is missing over h. And now let's simplify. Well, whenever I want to simplify, I can't cancel terms, but I can cancel factors. So let's factor an h because all of those have an h in common. And I get 2x plus h plus 1, right? If I factor out an h divided by h. And now, because h is a factor, factor means it's multiplied, I can cancel h over h. And my final answer becomes 2x plus h plus 1. So that is the difference quotient, and that is what f of x plus h minus f of x over h equals. And it doesn't seem like it's an important thing, but it's actually a very important thing. Okay, so we're getting close. Well, maybe not. So we have a vertical line test. So if we want to find something's a function and we have a graph, these are backwards. So sorry, this is a mistake. This is a function and this is not a function. Okay, so here, so let's read it. A graph in the Cartesian plane is the graph of a function if and only if no vertical line intersects the graph in more than one place. So if I look at this first one, every vertical line, all these green lines are vertical lines, and every one of them just hits that graph in one place, which makes it a function. And over here on the right, if you notice where this dotted line is right here, it actually hits the graph in 3 places. This has 3 points for the same x. And remember, I said for a function, for every x, there's only one y, and we can see that for whatever that x is, there's 3 different y values, which makes it not a function. It's still a relation, it's just not a function. So if we look at A, B, and C, well, underneath it, they've drawn vertical lines, and we can see that this is a function because there's no vertical line that passes through more than one point. And for B, this is also a function. And the reason they're telling you to look at x equals 2 underneath here is because it's a function till I get to that place where it splits, and then it's a function after. But right at this point here at 2, Well, it's open for this one's an open circle and this one's a closed circle. So still at x equals 2, there's still only one value because the open circle means that that value doesn't exist there. So that would make this also a function. However, for C, it really doesn't matter where I put my vertical line, unless I put it right here at the edge. It's the only place it's not going to hit 2 points, right? Every place else I put a vertical line is going to hit 2 points, which means this is not a function. It can only pass through 1 point for every x. And when I make a vertical line, I'm saying at this x, at this x, at this x. Okay, so we've talked about polynomials, and I gave you a different definition, and it's the same, but I think a little easier to deal with. So everything that's multiplied together is called a term. These are all terms. Term. Okay, and so on. Okay, so I'm just going to talk about each term. So for something to be a polynomial, each term has to consist of ax to the n, where, and again, the same, all the a's are real numbers. So the reason they write it like this with all these different subscripts is they're saying they're just different values. They could be the same, but they could be different. So we just don't know. So we're going to talk about them all as different numbers. So A is a real number, and it's also called the coefficient. Okay? And N is the exponent, and it has to, so we're talking about the exponent, and it has to be an integer. And again, we talked about integers. They're any whole number, negative infinity to positive infinity, but not fractional, not decimal. So it would be -2, -3, -4, 0, 1, 2, 3, 4, any whole number. 3.5, no, that's not a whole number. That's not an integer. Okay, so it has to be an integer greater than or equal to 0. Okay, and this is called the degree. All right, so now we're going to look and see, determine whether the, oh, and also I want to say this is in standard form. Standard form for a polynomial is we start at the highest exponent and go down. So if I look at this next picture, this is not in standard form. I recommend you make it in standard form. So how do I make it in standard form? I look at the exponent and I put the biggest exponent first. So this would be 5x to the third, and then minus 3x squared plus 7. So these are the same. Now that's in standard form. Okay. So determine whether the following functions are polynomial functions. Well, remember we have ax to the n. Well, that fits. But if you notice, there's really no x with the 7. That's because it's invisible. I know that you're going to think that's crazy, but pretend there's an x to the 0 here. Anything to the 0 power is always equal 1 as long as b is not equal to 0. Okay, so I do have an x there, but it's equal to 1, and 1 times 7 is 7. So we don't put it in, but just so that you can see that it's there, I want you to see that it's there. And in the previous slide, I said it's an integer greater than or equal to 0. Well, this is an integer, 0, greater than or equal to 0. Yeah, it's equal to 0. So this is a polynomial. Yes, it is a polynomial. So determine whether the following functions are polynomials. This is a polynomial. If the function is a polynomial, state the degree. The degree is the largest exponent. That's why it's always good to put it in standard form. So the degree of this is 3, and I'm getting that from my largest exponent. And that's basically all they're asking. So again, for this one, now notice our variable is t. So I can say this is the same as minus 11 times t to the 0 power, which is still 1, which makes it a polynomial with degree 0, because that's the only thing I have, and that's it. Okay. Now, the last one, I just want to make sure that some of you know the algebra rules for what 1 over t is, because if you don't, you wouldn't understand. But if you have something to a negative exponent, so some base to a negative exponent, that's the same as 1 over b to the m. If I have 1 over b to the m, sorry, negative m, it's the same as b to the m. So really what happens is if it's negative in the numerator, it becomes positive in the denominator. If it's negative in the denominator, it becomes positive in the numerator. Or I could say, if it's negative on the top, it becomes positive on the bottom. If it's negative on the bottom, it becomes positive on the top. So that's basically the rule for exponents, which means this is really the same as 3t to the 6th plus t to the negative 1 power, right? Because t to the negative 1 would be 1 over t. Well, remember from our definition, which I think is here, yes, n is an integer greater than or equal to 0. And I'm here, and I have n is negative 1. So this is not a polynomial. And since it's not a polynomial, then it is, we don't have to worry about the degree because it doesn't have a degree, only polynomials have degrees. Okay, so hopefully now you know what a polynomial is. Now we're going to talk about what a rational function is, which we already have talked about, but we're going to do it again. So a polynomial, a rational function is of this form where both g and x are polynomials. And remember, actually, this is not correct. Let's see if I can fix it. Yes. This is h of x. Make it small h. Okay. So here we have where h of x is not equal to 0 because we can't have the denominator equal to 0. Let me make these a little bigger. Better. Okay, so h of x cannot be equal to 0. The denominator can't be 0. And the degree of the denominator is greater than 0. Well, why do we have to add that the degree has to be greater than 0? The reason is because if I wrote f of x is equal to x squared plus 2x plus 1 over 3. Now the degree is 0, right? In the denominator. But I can write this as 1/3 x squared plus 2/3 x plus 1/3, right? And now this is really just a polynomial because 1/3 is the coefficient and it's a real number. and then we just have x squared x, and so on. So unless you have some variable in the denominator, it's not a rational function. You have to have a variable in the denominator. This is just a polynomial. Okay, because the degree of 3, let's see, because the degree of, I'll write h of x, which is equal to 3, the degree of this is 0. So because it's 0, it's not a rational function. It's still a polynomial, okay? And then we have root functions. So again, I'm going to teach you a little bit of algebra in case you don't know it. But what this root means is, so if you have the nth root, so that's the index of some function, let's say we have it to the m power, that's the same as the nth root of g of x, the whole thing to the m power. Or you can say this is the same as g of x to the m over n power. Okay, so let me see if I can kind of make this look a little more palatable. So first of all, if there's no n, we assume it to be 2. That's all. When you say square root, you won't see an index. You won't see that n, but it will be a 2. Otherwise, you'll have a value there. Now, let me show you why this is true in case you don't understand. So we're going to use this rule that says if I take a base to a power to a power, then this is equal to b to the m times n. So when we have a base to a power, we multiply the powers. So let's start here. I'm gonna do these 3 things. I'm gonna show you that they're equal. So if I take the, let's say this is the cube root of g of x squared. Well, this is equal to, and I'm going to use this final answer, g of x to the m is 2 and n is 3. So this is the same as g of x to the 2/3 power. If I were to say the cube root of g of x, and then I have the whole thing squared, well, that's like saying I have g to the 1/3 power, because there's a invisible 1, squared. And if I use my exponent rule, that means I multiply exponents. So this is equal to g, and then 1/3 times 2 is 2/3. So notice they're all the same. These are all equal to each other. And it's very important to be able to understand that and just kind of use it. To calculate things, usually this is the easiest way. It's easier to make things smaller and then bigger than to make things bigger. So this would, if I use this middle one, I'm gonna make that value smaller. So say g of x is the square root of 4, that would be 2. And then let's say m is 3, so it would be 2 to the 3rd power, right? Which is 8. That's if I use that. If I use this and I say g of x equals 4, and I should write all this down here. So if I want to know what the square root of 4 to the 3rd power is, well, I first have to calculate 4 to the 3rd power, and then I'd have to take the square root of it. So 4 to the third power is 64. So this would be the square root of 64, which is equal to 8, right? 4 times 4 is 16, times 4 is 64. Yes. So imagine if it was 15 to the third power. It's harder, right? But what's easier to do is say, let's take the square root of 4 to the third power. That's like the middle one. Well, now I know what the square root of 4 is 2. 2 to the third power is a lot easier to calculate. It's just 2 times 2 times 2. So that kind of gives you an overview of roots. So we're going to talk about different things about roots in a minute. We're going to do some problems. First, I want to go over this chart real quick. We already talked about almost all of it. So let's do it. So if you have a polynomial, and we now know what polynomials look like. I gave you a little simpler form, but that's the form they're using. The domain is always all real numbers from negative infinity to infinity. There's not any values that I can't use an x if I have a polynomial. Okay, so that's always true. For rational functions, if I want to find the domain, I can say it's all real numbers, but the denominator cannot equal 0, right? So that's important. That's an important thing. I have to make sure that my denominator is never 0. Polynomials don't have variable denominators. They'll only have numbers. So you don't have to worry about the denominator. That's why it's always true. So root functions, we'll actually do some of those problems in a minute, but there's two different things. If n is even, then we have to make sure that whatever's under this radical, this g of x, is greater than or equal to 0, because we can't take like the square root of a negative number, right? However, if it's odd, well, we can take the cubed root of an odd, of a negative number. For example, let's say I have the square root of -4. Well, it can't be 2. Let's try 2. If x equals 2, 2 times 2 is 4. That's not going to be right. So let's try x equals -2. Well, -2 times -2 is still +4. So we can't take the square root of a negative number. It will not be a real number. And that's all we're talking about in this class is real numbers. But if I take the cube root of -8, well, this does equal -2, because so how do I find out what the cube root is? It's the same number 3 times together equals that number. So I can say here, -2 times -2 times -2. Well, -2 times -2 is +4 times -2 is -8. Sorry about that noise. Something is not going well with my, one of my USB ports is weird. So that's why it's making that noise, and I don't want to stop right now. We're almost done. So when it's odd, the domain is all real numbers. So the domain is all real numbers. Okay, so let's see how that works in our examples. So first thing, we want to classify these. Is the first one a polynomial, a rational function, or a root function? Well, it's a polynomial. First of all, it has no denominator, and so it can't be a rational function. It has no radical, so it can't be a root. So this is a polynomial. And then find the domain. Well, we already just learned that every polynomial, the domain is from negative infinity to positive infinity, and that's in interval notation. Okay. Now for B, actually, I'm going to get a new slide. Hold on. I think I lost my mouse. Yeah, hold on 1 second. Okay, I did get my mouse back. Let's put in a new slide here. And let's copy over. Okay, so now we want to figure out, is this a polynomial? No, it has a denominator. Is it a polynomial over a polynomial? Yes, it is. A polynomial over a polynomial is a rational function. Okay, and now what I want to do is I want to figure out what the domain is. Well, the numerator can be anything, but we have to make sure that this denominator, the denominator, cannot equal 0. So how do I find out when it equals 0? Well, I said it equals 0. X squared minus x minus 6 cannot equal 0. Well, let's factor it. So if I factor it, I get x minus 3 times x plus 2. And again, that can't equal 0. So now I can figure out, well, x minus 3 cannot equal 0, because if it did, then the whole thing would equal 0. And x plus 2 cannot equal 0, because if it did, then the whole denominator would equal 0. So x cannot be equal to 3, or x cannot be equal to -2. Okay. So now how do I put this in interval notation? Here's my best recommendation. Draw this on a number line. Okay. And what I do is I'll just make this 0. I'll make this -2, make this +3. And it can't be those things. So I'm going to put open circles there, right? Because those are two numbers that it cannot be. But it can be anything else. So if I look on my number line, this is really what the number line for that denominator looks like. And that's the only thing I'm concerned about, because the numerator does not ever give me a problem. So I'm going to call this interval 1, interval 2, and interval 3. So I have 3 separate intervals because they don't connect, because I have those open circles, right? So I have to figure out, is it positive or negative? Well, the only way to do that is to actually plug in a number. Believe it or not, you can't just say those things are greater than 0, because if, for example, if this is positive and this is positive, then I get a positive number, right? Actually, I don't need to, no, this is, I'm talking about something completely different, so never mind. So I'm just going to take this and put it in interval notation. And in interval notation, interval 1 goes from -infinity to -2. And it doesn't include -2. Remember, there's that open circle. Union, and then I'm going to use interval 2, which goes from -2 to -3. And it doesn't include, sorry, to +3. And it doesn't include either any of those numbers, right? So -2 and +3 are not included. Union, and then I start at 3 and I go to infinity. And that's the answer in interval notation for the domain. This is the domain. So I just basically drew it on a number line. Once I draw it on the number line, I think it's a lot easier to get this interval notation. I have a lot of times seen people miss that middle interval if they just try to do it without the number line. They'll just get the two end pieces. So I do highly recommend a number line. And then our last question is C, like what is C? Well, we can see that C is a root function because it has the radical. Actually, C and D are both root functions, right? But I have to make sure that x squared minus 2x minus 8 is greater than or equal to 0. And that's basically what this chart says. So if it's even, the domain is the solution to the inequality g of x is greater than or equal to 0. So that's what I'm saying here. Okay. So the first thing I have to do is I do have to factor, because I do have to find my zeros. So I say this is x minus 4 times x plus 2. And we want this to be greater than or equal to 0. And again, I say, here's a number line. And first thing I do is I put on my number line my zeros, okay? Because to go from positive to negative, no matter what the graph looks like, let's say the graph looks like this, if I'm going from positive to negative, I'm always going through 0, right? So I want to find out where my zeros are because that'll tell me what's like where what my possibilities are for where it can change from positive to negative or negative to positive. If it doesn't touch 0, it's going to either stay all negative or all positive. So let's again say my zeros are x equals 4 or x equals -2. Those are my zeros. So here's 4 and here's -2. And since I got everything smushed pretty close together, I'm going to come down and I'm going to say, here's my 0 and here's my 0, right? And honestly, it can be greater than or equal. So I don't want to put open circles, but I am going to put circles there. And then I still have all those intervals. I still have first interval, second interval, third interval. Okay. Now we want to see in the first interval, is it positive or negative? And the best way at this moment, since you don't know how to do a lot of other things, I haven't taught you, I'm not going to show you the other way. So this is the way you have to do it. So I can see that I have these different intervals, right? So if this is, wait, I did something wrong here. Oh, I know it. These are interval 1, interval 2. Those are not things on the number line. And interval 3. And this is the number line of the equation. The one above it is just a number line. So let's look at interval 1. So interval 1 is from -2 to all the way down to -infinity. So what I want to do is I want to pick, let's say x equals -3. So if x equals -3, and you can either go back and plug it in here. A lot of times it's easier to plug it in here because all I really want to know is it positive or negative. So if I plug -3 into this equation right here, then -3 minus 7, that's a negative number. Let's see. So this is a negative number times, well, when x plus 2, I plug in -3, I get -1. So that's also a negative number. Negative times a negative is a positive. So from -infinity to 2, I get a positive number, which is greater than or equal to 0, right? Next, I want to plug in some number between -2 and 4 in this second interval. So I'm just going to pick x equals 0 because 0 is always the easiest. And if I plug 0 into this equation right here, what I'm plugging it into is this. So I get -4, which is negative, and then and then I get +2, so that's a positive. Negative times a positive is a negative, which makes my second interval negative, because 0 is in my second interval. And last, I have to do something with my third interval. So my third interval starts at 4, right? And it goes all the way to the left. So let's make x equal 5. So when x equals 5, and I plug it in here, I get 5 minus 1, which is a positive number. I get a positive number times when x equals 5, and I plug it into x plus 2, I also get a positive number. So this becomes a positive number, which means here it's positive. So now I know kind of how my intervals are separated. I think I'm going to have to do the next one on a new slide. I don't have enough room. This is the last problem, so let's just do it. Cut. And I don't know what that came from. Let's move this. All right, now let's see whatever that is. Let's get rid of that. Okay. So I hope you understand what I did here. Let me go back through it. I factored, I found my zeros. Here are my zeros. My zeros are at -2 and +4. And then I just plug numbers in on each interval. There's 3 intervals because -2 and 4 are like dividing up this number line. And I want to know in each division, is it positive or negative? So I'm looking for positive because I'm looking for x minus 4 times x plus 2 is greater than or equal to 0. And that means it's a positive number. So I know it's positive from -infinity to -2 because it says it right on my number line. But I do include the 0, which is at -2, because the square root of 0 is 0. So I include -2. That middle interval, actually, I'm going to erase these. I think these are definitely not helping. So now I look at the middle interval and it's negative. I don't want a negative number. I discard it. And then I look at the final interval, which is right here, the most right interval, and it starts at 4. So let's say, oh, I already plugged in 5. I know it's positive. So I start at 4. It does include 4 because 4 is a 0. So we do include it. And I go all the way to +infinity. And that is the domain of this function. So with radicals, what you need to do is take what's under the radical and make sure that it's greater than or equal to 0. And that is the most important thing. And remember, there's this invisible 2, so that means it's even, so we have to follow the rules of even. Now this one, again, we know it's a root function, but now the index equals 3, which is odd. And what did we say about odd radicals? The domain is all real numbers. Because I can put in, I can make, it could be a positive number, it could be a negative number, or it could be 0, like I showed you here. When I have an odd root, I can have a negative value. So, and then this chart also helps. It says if n is odd, which it is, then the domain is a set of all real numbers. So here, it's a set of all real numbers. I don't have to do any algebra. It's just done. It's an odd root, and it's negative infinity to positive infinity. The only thing you have to be careful of is if it's in the denominator, you have to take out where it's 0. But other than that, that's all you have to do. And that does conclude 3.1. Thank you for watching, and have a great day.